26 bytes, not megabytes, not kilobyte. That's the size of the weight we need to train a model to achieve a state-of-the-art performance in math. If you have told me years ago or even last month that you trained a 7 billion parameters like Qwen 2.5 that already achieving like 76% on math, and you push it to a state-of-the-art performance of 91% by only training a size of the model that is less than a Windows 95 desktop icon, I would have laughed at you and said that you were hallucinating. My entire career in AI, through my PhD and training high-scale AI solution, what I've learned is that basically the intelligence is heavy. So if you want to change a model behavior meaningfully, you need it to be smarter at reasoning. You need millions of parameters. You need, for example, a 64 LoRA adapter, and you need basically massive compute. But in this new paper from Meta, learning to reason in 13 parameters, this just shatters this intuition, and it doesn't just break it, it completely creates a new mental model for how actually language models actually learn. Today I want to walk you through 3 core ideas of this paper and explain how is it possible that we are going to cover TinyLoRA architecture, the information density hypothesis that explain how and why RL can actually outperform supervised fine-tuning, and talk about the paradox about the model scaling that suggests that the bigger your model is, it's going to require less number of parameters to train them. So without further ado, let's jump right into it. Welcome everyone to the channel, AI Fun Fact for All. For those of you who are in this channel, my name is Pedram. I have a PhD in computer science, and in this channel we talk about AI and machine learning and how we can use it in order to improve our efficiency. So let's go into part 1 of this TinyLoRA paper. So the myth of capacity. So we usually think about fine-tuning as injecting knowledge. So if we want a model to learn about biology, we give it biology book. If we want it to learn to reason, we show it learning traces. So it requires basically capacity, the bits and bytes, to actually store this information. But the author of this paper challenges this by introducing TinyLoRA. So you are probably aware of LoRA or low-rank adaptation. That's basically you freeze the big weights of the model and train 2 smaller matrices A and B to approximate these updates. Even at rank 1 of LoRA, 7 billion parameters, there's still millions of parameters. But TinyLoRA actually go completely extremes. Instead of training matrices, they actually train a tiny vector or sometimes even single parameters, and they project up the full model dimension by using a fixed frozen random matrices. What they're essentially saying is that what if the entire model share one learnable variable? So they tested this on Qwen 7 billion parameter using the GSM 8K on math benchmark. The result, they reach 91% accuracy using only 13 trainable parameters. In BFlow 16 format, this is just 26 bytes of information. So this forces us to confront the hard truth. We aren't teaching the model math, so the math is already there. The model is actually a library containing every single book ever written, but the lights are off. So the 13 parameters aren't writing new books, they're just finding the light switch. But here's a catch that kind of leads us to part number 2, which is the signal to noise ratio. So the 13 parameters trick only work if we are actually using reinforcement learning, and more particularly GRPO. If you want to do this with the supervised fine-tuning, the standard way that we almost do everything, it will fail. And the reason is when we train the supervised fine-tuning with this tiny parameters budget, the performance barely actually budge, and it only hit around 83%. To match the RL performance, SFT requires 1,000 times more parameters. But why? This is the most profound takeaway for any of you that are working on alignment. think about it like this. During my PhD, I had a professor that rambled a lot. If I was going to transcribe everything that he said, like supervised fine-tuning, it would feel most like notebooks with ums and ahs and irrelevant stories. I will also need a lot of storage to actually capture them. But if I just focused on passing the exam like RL, I didn't need to memorize this. I just need to know a binary signal. Did I get the answer right or wrong? So the paper argues that SFT is actually noisy. When you show a model a chain of thought solution, the model doesn't know which part of the answer is actually crucial reasoning component and which part are just stylist fluff. So it tries to memorize everything. So this requires a massive bandwidth. However, on the other hand, RL is actually different. So the reward signal is actually sparse, but it's very clean. So it filters out the noise and it only updates the weight when it actually correlates with the correct answer. So it ignores the style, the fluff, and the noise. So because this signal is so pure, it can compress the lesson that they want to understand to a very tiny and efficient update. This brings me to part number 3, the inverse scaling law. This is the part that makes me most optimistic about the future of local LLM. So the researcher found that there is a trend that seems backward. So if you have a base model and you increase the number of parameters, the number of parameters that you need to fine-tune them actually decreases. So a 70 billion parameters need fewer number of trainable parameters to steer compared to a 7 billion parameter. The intuition is this: a larger model have a lower intrinsic dimension, so they are already so capable, so dense with potentials, and they are incredibly sensitive to steering. So they are like high performance sport cars that they don't need you to hurt a lot to actually turn them. You just need a fingertip. So the others suggest that for even a trillion parameters that will come in future, in order to make them fully steerable for complex tasks, you just need a handful of parameters. Now let's wrap up. During the past few years, we are obsessed with data engineering, curating massive data for SFT, but these papers suggest that for reasoning tasks at least, we might hit a wall with this approach. If you want to force feed the model noises when you should actually give them a compass. So these 26 bytes didn't teach the Qwen how to actually do add or subtract. They just align its internal state to produce longer chain of thoughts. They unlock this behavior, and that is how I changed my mental model today as well. So we thought that we need millions of ways to change a model behavior, but we were wrong. We just need to filter out the noise. Let me know in the comments, what do you guys think? Is the future of supervised fine-tuning dead for alignment, or do you still need them for pre-training before actually having the RL? If you enjoyed the video, make sure to like it. More importantly, subscribe to the channel. If you like the video, I think you will also love this one that I created about how Google actually introduced recursive language model to combat the context rot, or you can watch this one that I explain by code how you can basically run your AI for coding completely for free in your agentic favorite models. Thanks for watching, and see you until the next one.